electricity comes out. It's pretty fantastic. You know, water comes in, you light it on fire, turn it to steam, and what comes out, this is invisible thing that's incredibly valuable. It took another 80 years to go to alternating current, but Dynamo is where it all started. Okay, so we decided to call this operating system, this piece of software, insanely complicated software, the NVIDIA Dynamo. It's open source, and we're so happy that so many of our partners are working with us on it. And one of my favorite partners, I just love them so much because of the revolutionary work that they do, and also because Aravin's such a great guy. But Perplexity is a great partner of ours in working through this. Okay, so anyhow, really, really great. Okay, so now we're gonna have to wait until we scale up all these infrastructure, but in the meantime, we've done a whole bunch of very in-depth simulation. We have supercomputers doing simulation of our supercomputers, which makes sense. And I'm now gonna show you the benefit of everything that I've just said. And remember the factory diagram. On the x-axis is tokens per second throughput, on the y-axis, tokens per second throughput of the factory, and the x-axis, tokens per second of the user experience. And you want super smart AIs, and you want to produce a whole bunch of it. This is Hopper. Okay, so this is Hopper, and it can produce for each user about 100 tokens per second. This is 8 GPUs. And it's connected with InfiniBand, and I'm normalizing it to tokens per second per megawatt. So it's a 1 megawatt data center, which is not a very large AI factory, but anyhow, 1 megawatt, okay? And so it can produce for each user 100 tokens per second, and it can produce at this level, whatever that happens to be, 100,000 tokens per second for that 1 megawatt data center. Or it can produce about 2.5 million tokens per second, 2.5 million tokens per second for that AI factory if it was super batched up and the customer is willing to wait a very long time. Okay, does that make sense? All right, so nod. All right, because this is where, you know, every GTC, there's the price for entry, you guys know. And it's like, you get tortured with math, okay? This is the only at NVIDIA do you get tortured with math. All right, so Hopper, you get 2.5. Now, what's that 2.5 million? How do you translate that? 2.5 million, remember, ChatGPT is like $10 per million tokens, right? $10 per million tokens. Let's pretend for a second that's I think the $10 per million tokens is probably down here, okay? I'd probably say it's down here, but let me pretend it's up there, because 2.5 million, 10, so $25 million per second. Does that make sense? That's how you think through it. Or on the other hand, if it's way down here, then the question is, you know, so it's 100,000, just divide that by 10, okay? $250,000 per factory per second. And then as it was 30 million seconds in a year, and that translates into revenues for that 1 megawatt data center. And so that's your goal. On the one hand, you would like your token rate to be as fast as possible so that you can make really smart AIs. And if you have smart AIs, people pay you more money for it. On the other hand, the smarter the AI, the less you can make in volume. Very sensible trade-off. And this is the curve we're trying to bend. Now, what I'm just showing you right now is the fastest computer in the world, Hopper. It's the computer that revolutionized everything. And so how do we make that better? So the first thing that we do is we come up with Blackwell with NVLink 8. Same Blackwell, that one same compute, and that one compute node with NVLink 8 using FP8. And so Blackwell is just faster. Faster, bigger, more transistors, more everything. But we like to do more than that, and so we introduce a new precision. It's not quite as simple as 4-bit floating point, but using 4-bit floating point, we can quantize the model, use less energy to do the same. And as a result, when you use less energy to do the same, you could do more. Because remember, one big idea is that every single data center in the future will be power limited. Your revenues are power limited. You could figure out what your revenues are going to be based on the power you have to work with. This is no different than, like many other industries. And so we are now a power limited industry. Our revenues will associate with that. Well, based on that, you want to make sure you have the most energy efficient compute architecture you can possibly get. Then we scale up with NVLink 72. Does that make sense? Look at the difference between that NVLink 72 FP4, and then because our architecture is so tightly integrated, and now we add Dynamo to it, Dynamo can extend that even further. Are you following me? So Dynamo also helps Hopper, but Dynamo helps Blackwell incredibly. Now, yep. Only at GTC do you get an applause for that. And so now notice what I put, those two shiny parts, that's kind of where your max Q is. That's likely where you'll run your factory operations. You're trying to find that balance between maximum throughput and maximum quality of AI. Smartest AI, the most of it. Those two, that XY intercept is really what you're optimizing for. And that's what it looks like if you look underneath those two squares. Blackwell is way, way better than Hopper. And remember, this is not ISO chips. This is ISO power. This is ultimate Moore's Law. This is what Moore's Law was always about in the past. And now here we are, 25x in one generation as ISO power. This is not ISO chips, it's not ISO transistors, it's not ISO anything. ISO power, the ultimate limiter. There's only so much energy we can get into a data center. And so within ISO power, Blackwell is 25 times. Now here's that rainbow. That's incredible. That's the fun part. Look, all the different underneath the Pareto, the frontier Pareto, we call it the frontier Pareto, under the frontier Pareto are millions of points we could have configured the data center to do. We could have parallelized and split the work and sharded the work in a whole lot of different ways. And we found the most optimal answer, which is the Pareto, the frontier Pareto, okay, the Pareto frontier. And each one of them, because of the color, shows you it's a different configuration. Which is the reason why this image says very, very clearly you want a programmable architecture that is as homogeneously fungible as possible, because the workload changes so dramatically across the entire frontier. And look, we got on the top, expert parallel 8, batch of 3000, disaggregation off, Dynamo off. In the middle, expert parallel 64 with the 26% is used for context, so Dynamo is turned on, 26% context, the other 74% is not. Batch of 64, and expert parallel of 64 on one, expert parallel 4 on the other. And then down here, all the way to the bottom, you got tensor parallel 16 with expert parallel 4, batch of 2, 1% context. The configuration of the computer is changing across that entire spectrum. And then this is what happens. So this is with input sequence length. This is a kind of a commodity test case. This is a test case that you can benchmark relatively easily. The input is 1,000 tokens. The output is 2,000. Notice earlier, we just showed you a demo where the output is very simply 9,000, right? 8,000, okay? And so obviously this is not representative of just that one chap. Now this one is more representative, and this is what, the goal is to build these next generation computers for next generation workloads. And so here's an example of a reasoning model. And in a reasoning model, Blackwell is 40 times the performance of Hopper, straight up. Pretty amazing. You know, I've said before, somebody actually asked, why would I say that? But I said before that when Blackwell starts shipping in volume, you couldn't give Hoppers away. And this is what I mean. And this makes sense. If you're still looking to buy a Hopper, don't be afraid. It's okay. But I'm the chief revenue destroyer. My sales guys are going, oh no, don't say that. There are circumstances where Hopper is fine. That's the best thing I could say about Hopper. There are circumstances where you're fine. Not many. If I had to take a swing. And so that's kind of my point. When the technology is moving this fast, and because the workload is so intense and you're building these things, they're factories, we really like you to invest in the right versions. Okay, just to put it in perspective, this is what a 100 megawatt factory looks like. There's a 100 megawatt factory. You have, based on Hoppers, you have 45,000 dies, 1,400 racks, and it produces 300 million tokens per second. Okay? And then this is what it looks like with Blackwell. You have 86, yeah, I know. That doesn't make any sense. Okay, so we're not trying to sell you less. Okay, our sales guys are going, Jensen, you're selling them less. This is better. Okay, and so anyways, the more you buy, the more you save. It's even better than that. Now the more you buy, the more you make. And so anyhow, remember, everything is in the context, everything is now in the context of AI factories. And although we talk about the chips, you always start from scale up. We talk about the chips, but you always start from scale up, the full scale up. What can you scale up to the maximum? I want to show you now what an AI factory looks like, but AI factories are so complicated. I just gave you an example of one rack. It has 600,000 parts. It's 3,000 pounds. Now, you've got to take that and connect it with a whole bunch of others. And so we are starting to build what we call the digital twin of every data center. Before you build a data center, you have to build a digital twin. Let's take a look at this. This is just incredibly beautiful. The world is racing to build state-of-the-art, large-scale AI factories. Bringing up an AI gigafactory is an extraordinary feat of engineering, requiring tens of thousands of workers, from suppliers, architects, contractors, and engineers, to build, ship, and assemble nearly 5 billion components and over 200,000 miles of fiber, nearly the distance from the Earth to the Moon. The NVIDIA Omniverse blueprint for AI factory digital twins enables us to design and optimize these AI factories long before physical construction starts. Here, NVIDIA engineers use the blueprint to plan a 1 gigawatt AI factory, integrating 3D and layout data of the latest NVIDIA DGX superpods and advanced power and cooling systems from Vertiv and Schneider Electric, and optimized topology from NVIDIA Air, a framework for simulating network logic, layout, and protocols. This work is traditionally done in silos. The Omniverse blueprint lets our engineering teams work in parallel and collaboratively, letting us explore various configurations to maximizing TCO and power usage effectiveness. NVIDIA uses Cadence Reality Digital Twin, accelerated by CUDA and Omniverse libraries, to simulate air and liquid cooling systems. And Schneider Electric with ETAP, an application to simulate power block efficiency and reliability. Real-time simulation lets us iterate and run large-scale what-if scenarios in seconds versus hours.
We use the digital twin to communicate instructions to the large body of teams and suppliers, reducing execution errors and accelerating time to bring up. And when planning for retrofits or upgrades, we can easily test and simulate cost and downtime, ensuring a future-proof AI factory.
This is the first time anybody who builds data centers says, oh, that's so beautiful. All right, I got a race here because turns out I got a lot to tell you. And so if I go a little too fast, it's not because I don't care about you, it's just I got a lot of information to go through. All right, so first, our roadmap. We're now in full production of Blackwell. Computer companies all over the world are ramping these incredible machines at scale. And I'm just so pleased and so grateful that all of you worked hard on transitioning into this new architecture. And now, in the second half of this year, we'll easily transition into the upgrade. So we have the Blackwell Ultra NVLink 72. It's 1.5 times more FLOPS. It's got a new instruction for attention. It's 1.5 times more memory. All that memory is useful for things like KV cache. It's 2 times more bandwidth, okay, for networking bandwidth. And so now that we have the same architecture, we'll just kind of gracefully glide into that, and that's called Blackwell Ultra, okay? So that's coming second half of this year. Now, there's a reason why this is the only product announcement in any company where everybody's going, yeah, next. Yeah. And in fact, that's exactly the response I was hoping to get. And here's why. Look, we're building AI factories and AI infrastructure. It's going to take years of planning. This isn't like buying a laptop. This isn't discretionary spend. This is spend that we have to go plan on. And so we have to plan on having, of course, the land and the power, and we have to get our CapEx ready, and we get engineering teams, and we have to lay it out a couple, 2-3 years in advance, which is the reason why I show you our roadmap a couple, 2-3 years in advance, so that we don't surprise you in May. Hi, in another month we're going to go to this incredible new system. I'll show you an example in a second. And so we plan this out in multiple years. The next click, 1 year out, is named after an astronomer, and her grandkids are here. Her name is Vera Rubin. She discovered dark matter. Okay, yep. Vera Rubin is incredible because the CPU is new. It's twice the performance of Grace, and more memory, more bandwidth, and yet just a little tiny 50-watt CPU. It's really quite incredible. Okay, and Rubin, brand new GPU, CX9, brand new networking smart NIC, NVLink 6, brand new NVLink, brand new memories, HBM4. Basically, everything is brand new except for the chassis. And this way, we could take a whole lot of risk in one direction and not risk a whole bunch of other things related to the infrastructure. And so Vera Rubin, NVLink 144, is the second half of next year. Now, one of the things that I made a mistake on, and so I just need you to make this pivot. We're going to do this one time. Blackwell is really 2 GPUs in one Blackwell chip. We call that one chip a GPU, and that was wrong. And the reason for that is it screws up all the NVLink nomenclature and things like that. So going forward, without going back to Blackwell to fix it, going forward, when I say NVLink 144, it just means that it's connected to 144 GPUs. And each one of those GPUs is a GPU die, and it could be assembled in some package. How it's assembled could change from time to time, okay? And so each GPU die is a GPU. Each NVLink is connected to the GPU. And so Vera Rubin NVLink 144. And then this now sets the stage for the second half of the year, the following year, we call Rubin Ultra. Okay, so Vera Rubin Ultra. I know. This one is where you go, all right, so this is Vera Rubin Ultra, second half of 27. It's NVLink 576, extreme scale up. Each rack is 600 kilowatts, 2.5 million parts, okay? And obviously a whole lot of GPUs. And everything is X factored more. So 14 times more flops, 15 exaflops. Instead of one exaflop, as I mentioned earlier, is now 15 exaflops, scaled up exaflops, okay? And it's 4.6 petabytes, so 4,600 terabytes per second scale up bandwidth. I don't mean aggregate, I mean scale up bandwidth. And of course, a brand new NVLink switch and CX9, okay? And so notice 16 sites, 4 GPUs in one package, extremely large NVLink. Now just put that in perspective. This is what it looks like, okay? Now this is going to be fun. So you are just literally ramping up Grace Blackwell at the moment, and I don't mean to make it look like a laptop, but here we go. Okay, so this is what Grace Blackwell looks like, and this is what Rubin looks like. ISO dimension. And so this is another way of saying, before you scale out, you have to scale up. Does that make sense? Before you scale out, you scale up. And then after that, you scale out with amazing technology that I'll show you in just a second. All right, so first you scale up, and then now that gives you a sense of the pace at which we're moving. This is the amount of scale up flops. This is scale up flops. Hopper is 1x, Blackwell is 68x, Rubin is 900x. Scale up flops. And then if I turn it into essentially your TCO, which is power on top, power per, and the underneath is the area underneath the curve that I was talking to you about, the square underneath the curve, which is basically flops times bandwidth, okay? So the way you think about a very easy gut check on whether your AI factories are making progress is watts divided by those numbers. And you can see that Rubin is going to drive the cost down tremendously. Okay, so that's very quickly NVIDIA's roadmap. Once a year like clock ticks, once a year. Okay, how do we scale up? Well, we were preparing to scale out. That was scale up, was NVLink. Our scale out network is InfiniBand and Spectrum-X. Most were quite surprised that we came into the Ethernet world. And the reason why we decided to do Ethernet is if we could help Ethernet become like InfiniBand, have the qualities of InfiniBand, then the network itself would be a lot easier for everybody to use and manage. And so we decided to invest in Spectrum. We call it Spectrum-X, and we brought to it the properties of congestion control and very low latency and a mountain of software that's part of our computing fabric. And as a result, we made Spectrum-X incredibly high performant. We scaled up the largest single GPU cluster ever as one giant cluster with Spectrum-X, right? And that was Colossus. And so there are many other examples of it. Spectrum-X is unquestionably a huge home run for us. One of the areas that I'm very excited about is the largest enterprise networking company to take Spectrum-X and integrate it into their product line so that they could help the world's enterprises become AI companies. We're at 100,000 with CX7. Now CX8's coming, CX9's coming, and during Rubin's time frame, we would like to scale out the number of GPUs to many hundreds of thousands. Now, the challenge with scaling out GPUs to many hundreds of thousands is the connection of the scale out. This connection on scale up is copper. We should use copper as far as we can, and that's, call it a meter or two. And that's incredibly good connectivity. very high reliability, very good energy efficiency, very low cost. And so we use copper as much as we can on scale up, but on scale out, where the data centers are now the size of the stadium, we're going to need something much long distance running. And that's just where silicon photonics comes in. The challenge of silicon photonics has been that the transceivers consume a lot of energy. To go from electrical to photonic has to go through a SerDes, go through a transceiver and a SerDes, several SerDes. And so each one of these, am I alone? Is anybody? What happened to my networking guys? Can I have this up here? Yeah, let's bring it up so I can show people what I'm talking about. Okay, so first of all, we're announcing NVIDIA's first co-packaged option silicon photonic system. It is the world's first 1.6 terabit per second CPO. It is based on a technology called micro-ring resonator modulator, and it is completely built with this incredible process technology at TSMC that we've been working with for some time. And we partnered with just a giant ecosystem of technology providers to invent what I'm about to show you. This is really crazy technology, crazy technology. Now, the reason why we decided to invest in MRM is so that we could prepare ourselves using MRM's incredible density and power, better density and power compared to Mach Zehnder, which is used for telecommunications when you drive from one data center to another data center in telecommunications, or even in the transceivers that we use Mach Zehnder, because the density requirement is not very high until now. And so if you look at these transceivers, this is an example of a transceiver. They did a very good job tangling this up for me. Oh, wow. Thank you. Oh, mother of God. Okay. This is where you got to turn reasoning on. It's not as easy as you think. These are squirrely little things. All right, so this one right here, this is 30 watts, just so keep you remember, this is 30 watts. And if you buy it in high volume, it's $1,000. This is a plug. On this side is electrical. On this side is optical. Okay, so optics come in through the yellow. You plug this into a switch. It's electrical. On this side, there's transceivers, lasers, and it's a technology called Mach Zehnder, and incredible. And so we use this to go from the GPU to the switch to the next switch, and then the next switch down, and the next switch down to the GPU, for example. And so each one of these, if we had 100,000 GPUs, we would have 100,000 of this side, and then another, 100,000, which connects the switch to a switch, and then on the other side, I'll attribute that to the other NIC. If we had 250,000, we'll add another layer of switches, and so each GPU, every GPU, 250,000, every GPU would have 6 transceivers. Every GPU would have 6 of these plugs, and these 6 plugs would add 180 watts per GPU, 180 watts per GPU, and $6,000 per GPU, okay? And so the question is, how do we scale up now to millions of GPUs? Because if we had 1 million GPUs, multiplied by 6, right, it would be 6 million transceivers times 30 watts, 180 megawatts of transceivers. They didn't do any math, they just moved signals around. And so the question is, how could we afford, and as I mentioned earlier, energy is our most important commodity. Everything is related ultimately to energy. So this is going to limit our revenues, our customers' revenues, by subtracting out 180 megawatts of power. And so this is the amazing thing that we did. We invented the world's first MRM micromirror, and this is what it looks like. There's a little waveguide. You see that on that waveguide goes to a ring. That ring resonates, and it controls the amount of reflectivity of the waveguide as it goes around, and it limits and modulates the energy, the amount of light that goes through. And it shuts it off by absorbing it or pass it on. Okay, it turns the light, this direct continuous laser beam, into ones and zeros. And that's the miracle. And that technology is then, the photonic IC is stacked with the electronic IC, which is then stacked with a whole bunch of micro lenses, which is stacked with this thing called fiber array. These things are all manufactured using this technology at TSMC called, they call it COUPE, and packaged using a 3D CoWoS technology, working with all of these technology providers, a whole bunch of them, the names I just showed you earlier, and it turns it into this incredible machine. So let's take a look at the video of it. Just a technology marvel. And they turn into these switches. Our InfiniBand switch, the silicon is working fantastically. Second half of this year, we will ship the silicon photonics switch in the second half of this year. In the second half of next year, we'll ship the Spectrum X. Because of the MRM choice, because of the incredible technology risks that over the last 5 years that we did, and filed hundreds of patents, and we've licensed it to our partners so that we can all build them. Now, we're in a position to put silicon photonics with co-packaged options, no transceivers, fiber, direct fiber into our switches with a radix of 512. This is the 512 ports. This would just simply not be possible any other way. And so this now set us up to be able to scale up to these multi-100,000 GPUs and multi-million GPUs. And the benefit, just so you imagine this is incredible. In a data center, we could save tens of megawatts. Let's say 10 megawatts, well, let's say 60 megawatts. 6 megawatts is 10 Rubin Ultra racks. 6 megawatts is 10 Rubin Ultra racks, right? And 60, that's a lot. 100 Rubin Ultra racks of power that we can now deploy into Rubins. All right, so this is our roadmap. Once a year, an architecture every 2 years, a new product line every single year, X factors up, and we try to take silicon risk or networking risk or system chassis risk in pieces so that we can move the industry forward as we pursue these incredible technology. Vera Rubin, and I really appreciate the grandkids for being here. This is our opportunity to recognize her and to honor her for the incredible work that she did. Our next generation will be named after Feynman. Okay, NVIDIA's roadmap. Let me talk to you about enterprise computing. This is really important. In order for us to bring AI to the world's enterprise, first we have to go to a different part of NVIDIA. The beauty of Gaussian splats. Okay, in order for us to take AI to enterprise, take a step back for a second and remind yourself this. Remember, AI and machine learning has reinvented the entire computing stack. The processor is different, the operating system is different, the applications on top are different. The way the applications are different, the way you orchestrate it are different, and the way you run them are different. Let me give you one example. The way you access data will be fundamentally different than the past. Instead of retrieving precisely the data that you want and you read it to try to understand it, in the future, we will do what we do with Perplexity. Instead of doing retrieval that way, I'll just ask Perplexity what I want. Ask it a question, and it will tell you the answer. This is the way enterprise IT will work in the future as well. We'll have AI agents, which are part of our digital workforce. There's 1 billion knowledge workers in the world. There are probably going to be 10 billion digital workers working with us side by side. 100% of software engineers in the future, there are 30 million of them around the world, 100% of them are going to be AI assisted. I'm certain of that. 100% of NVIDIA software engineers will be AI assisted by the end of this year. And so AI agents will be everywhere. How they run, what enterprises run, and how we run it will be fundamentally different. And so we need a new line of computers. And this your GeForce. Okay, so this is called DGX Station. DGX Spark and DGX Station are going to be available by all of the OEMs. HP, Dell, Lenovo, Asus. It's going to be manufactured for data scientists and researchers all over the world. This is the computer of the age of AI. This is what computers should look like. And this is what computers will run in the future. And we have a whole lineup for enterprise now, from little tiny one to workstation ones, the server ones to supercomputer ones, and these will be available by all of our partners. We will also revolutionize the rest of the computing stack. Remember, computing has 3 pillars. There's computing, you're looking at it. There's networking, as I mentioned earlier, Spectrum X going to the world's enterprise, an AI network. And the third is storage. Storage has to be completely reinvented. Rather than a retrieval-based storage system, it's going to be a semantics-based retrieval system, a semantics-based storage system. And so the storage system has to be continuously embedding information in the background, taking raw data, embedding it into knowledge, and then later when you access it, you don't retrieve it, you just talk to it. You ask it questions, you give it problems. And one of the examples, I wish we had a video of it, but Aaron at Box even put one up in the cloud, worked with us to put it up in the cloud. And it's basically, a super smart storage system. And in the future, you're going to have something like that in every single enterprise. That is the enterprise storage of the future. And we're working with the entire storage industry, really fantastic partners, DDN and Dell and HP Enterprise and Hitachi and IBM and NetApp and Nutanix and Pure Storage and VAST and Weka. Basically, the entire world storage industry will be offering this stack. For the very first time, your storage system will be GPU accelerated. And so somebody thought I didn't have enough slides. And so Michael thought I didn't have enough slides. So he said, Jensen, just in case you don't have enough slides, can I just put this in there? And so this is Michael's slides. But he sent this to me. He goes, just in case you don't have any slides. And I got too many slides. But this is such a great slide. And let me tell you why. In one single slide, he's explaining that Dell is going to be offering a whole line of NVIDIA enterprise IT AI infrastructure systems and all the software that runs on top of it. Okay, so you can see that we're in the process of revolutionizing the world's enterprise. We're also announcing today this incredible model that everybody can run. And so I showed you earlier R1, a reasoning model. I showed you versus Llama 3, a non-reasoning model. And obviously R1 is much smarter. But we can do it even better than that. And we can make it possible to be enterprise ready for any company. And it's now completely open source. It's part of our system we call NIMS. And you can download it. You can run it anywhere. You can run it on DGX Spark. You can run it on DGX Station. You can run it on any of the servers that the OEMs make. You can run it in the cloud. You can integrate it into any of your agentic AI frameworks. And we're working with companies all over the world, and I'm going to flip through these, so watch very carefully. I've got some great partners in the audience. I want to recognize Accenture, Julie Sweet and her team are building their AI factory and their AI framework. Amdocs, the world's largest telecommunications software company. AT&T, John Stankey and his team building an AT&T AI system, agentic system. Larry Fink and BlackRock team building theirs. Annie Rood. In the future, not only will we hire ASIC designers, we're going to hire a whole bunch of digital ASIC designers from Anirudh Cadence that will help us design our chips. And so Cadence is building their AI framework. And as you can see, in every single one of them, there's NVIDIA models, NVIDIA NIMs, NVIDIA libraries integrated throughout so that you can run it on-prem, in the cloud, any cloud. Capital One, one of the most advanced financial services companies in using technology, has NVIDIA all over it. Deloitte, Jason and his team, EY, Janet and his team, NASDAQ, and Adina and her team, integrating NVIDIA technology into their AI frameworks. And then Christian and his team at SAP, Bill McDermott and his team at ServiceNow. That was pretty good, huh? First, this is one of those keynotes where the first slide took 30 minutes, and then all the other slides took 30 minutes. All right, so next, let's go somewhere else. Let's go talk about robotics, shall we? Let's talk about robots. Well, the time has come. The time has come for robots. Robots have the benefit of being able to interact with the physical world and do things that otherwise digital information cannot. We know very clearly that the world has severe shortage of human laborers, human workers. By the end of this decade, the world is going to be at least 50 million workers short. We'd be more than delighted to pay them each $50,000 to come to work. We're probably going to have to pay robots $50,000 a year to come to work. And so this is going to be a very, very large industry. There are all kinds of robotic systems. Your infrastructure will be robotic. Billions of cameras in warehouses and factories, 10, 20 million factories around the world. Every car is already a robot, as I mentioned earlier, and then now we're building general robots. Let me show you how we're doing that.
Everything that moves will be autonomous. Physical AI will embody robots of every kind, in every industry. 3 computers built by NVIDIA enable a continuous loop of robot AI simulation, training, testing, and real-world experience. Training robots requires huge volumes of data. Internet-scale data provides common sense and reasoning, but robots need action and control data, which is expensive to capture. With blueprints built on NVIDIA Omniverse and Cosmos, developers can generate massive amounts of diverse, synthetic data for training robot policies. First, in Omniverse, developers aggregate real-world sensor or demonstration data according to their different domains, robots, and tasks. Then use Omniverse to condition Cosmos, multiplying the original captures into large volumes of photoreal, diverse data. Developers use Isaac Lab to post-train the robot policies with the augmented dataset. And let the robots learn new skills by cloning behaviors through imitation learning, or through trial and error, with reinforcement learning AI feedback. Practicing in a lab is different than the real world. New policies need to be field tested. Developers use Omniverse for software and hardware-in-the-loop testing, simulating the policies in a digital twin with real-world environmental dynamics, with domain randomization, physics feedback, and high-fidelity sensor simulation. Real-world operations require multiple robots to work together. Mega, an Omniverse blueprint, lets developers test fleets of post-trained policies at scale. Here, Foxconn tests heterogeneous robots in a virtual NVIDIA Blackwell production facility. As the robot brains execute their missions, they perceive the results of their actions through sensor simulation, then plan their next action. Mega lets developers test many robot policies, enabling the robots to work as a system, whether for spatial reasoning, navigation, mobility, or dexterity. Amazing things are born in simulation. Today, we're introducing NVIDIA Isaac GR00T N1. GR00T N1 is a general model for humanoid robots. It's built on the foundations of synthetic data generation and learning in GR00T N1 features a dual system architecture for thinking fast and slow, inspired by principles of human cognitive processing. The slow thinking system lets the robot perceive and reason about its environment and instructions, and plan the right actions to take. The fast thinking system translates the plan into precise and continuous robot actions. GR00T N1's generalization lets robots manipulate common objects with ease